A confirmation regarding the audio, please, guys. If you're able to hear me out perfectly well, kindly confirm the same. Thank you. We shall be starting in a couple of minutes, guys. So, hello, a very warm good evening to all of you, and welcome to Baiju's Exam Prep. Welcome to another session of Geography, where today we shall be picking up where we left off yesterday. So, today we shall be picking up the threads after the portion of the continental drift theory. Now, here, yesterday, what is it that we had discussed? So yesterday we had held a discussion with regards to the rocks, the various different types of rocks. How is it that we have the formation of the igneous rocks, the types and the varieties that you can have for the igneous rocks types? Also, what do we mean by sedimentary and metamorphic rocks? Their examples and their types, their formation. That is something that we looked at. After that, we initiated the discussion with regards to the continental drift theory, where we had discussed that what this continental drift theory is. It was propounded by Alfred Wagner. And basically, we also looked at why is it that Wagner came upon this particular theory. So there we discussed the set of evidences that was produced by Alfred Wagner, whereby Wagner relied on the set of evidences based on geological evidences, paleontological evidences, and climatological evidences as well, whereby he came to a conclusion that the continents, sometime in the geological history or the past of the planet, all the continents were one, and eventually they broke off into different parts, and that is what the continents are still drifting today, and that is where we have the present day shape of the continents and oceans. We also saw that while the evidences pointed out by Wagner were to the point, and the evidences were significantly important in the sense that all of the evidences pointed to the movement or the drifting of the continents, but the assumptions and the reasons that Wagner basically undertook in order to show or in order to prove his theory, those assumptions and those reasons, they themselves are not fully satisfactory. So that is where Wagner's continental drift theory was significantly rejected. But nonetheless, at that point of time, this continental drift theory was still remarkable with its approach when we talk about it, that how for the first time someone elaborated upon the aspect that yes, the land that we are standing upon, the continents that we are standing upon, these continents indeed are in motion. So that is something that we took a look at yesterday. Now, today, what is it that we are going to talk about? So, today we are going to talk about the aspect of convection current theory. Then we are going to talk about the seafloor spreading theory. And then we will enter into the portion of plate tectonics. Now, convection current theory is where we shall be initiating the discussion from. Now, please understand, some learning from the continental drift, some learning from the convection current, some learning from seafloor spreading. All these learnings that we gain from these different theories, eventually that is something which helped us understand and basically helped the various geographers postulate the plate tectonic theory, which is the modernist theory, which is the most acceptable theory. So here our purpose is very simple, very basic. Our purpose is to be able to understand what these theories they did right, and how all these theories pointed us in the direction of what the real picture is. For example, when we talk about the continental drift theory, Even though the contribution of continental drift theory can always be in a way ignored, that yes, the reasons were false, the assumptions were false, but nonetheless it showed the entire world a path to a direction whereby they can say that yes, the continents that we are standing upon, that is moving. Now then we come to the portion of convection current theory. This convection current theory, this was provided and postulated by whom? This was postulated by Sir Arthur Holmes. Arthur Holmes. Now, Sir Arthur Holmes, if you try to explore his background, if you try to explore, now obviously I don't want you to do that because you have other subjects to study as well. I understand that you have a lot of work pressure already with you, so I'm not going to tell you to explore each one of them individually. That is the last thing that I would want out of you. But still, nonetheless, if you explore that, what is it that Sir Arthur Holmes specialized in? He was a renowned physicist of his time. So the aspect of physics and the aspect of science relating to the movement of particles, etc., that is something that Arthur Holmes really specialized in. Now, he provided a convection current theory. Now, with this theory, please understand that Sir Arthur Holmes was not trying to prove anything. He was not trying to prove that, okay, this is how the continents would have come into existence, or there was no such reference with regards to the movement which happens on the surface. This theory was very simple. This theory was based upon the basics of convection current. Now, before anything, let us assume that we don't know anything about convection current. And what do we mean by convection current? Let us assume we have absolutely zero clue, because I understand many of us, we are not from science background. So let us first of all understand, what do we mean when we talk about a convection current? Now for this, I want you to recall the moment that any point of time, maybe in your life at any point of time, or even on your day-to-day activities, if you have entered the kitchen and the bare minimum that you have done is, let's say, boil a utensil full of milk or boil water in a utensil, you would have observed this convection current. We don't realize this, that what a convection current is, right? But then when you boil water, when you put a utensil on the gas stove and you put it and you fill it with water and you put it on boil, what is it that you observe? You will observe that after some time the bubbles, they start rising, it starts bubbling. But have you ever observed the origin of those bubbles? Where do those bubbles come from? So that is the aspect of convection current. Let us understand how, what, why, and when. So for example, let's suppose here, Hitesh, in case you are uncomfortable with using Sir Arthur Holmes, just write Arthur Holmes. There is no compulsion of writing Sir Arthur Holmes here. Anyways, this convection current theory is relevant only for your prelims. Okay, for optional guys, this is something which is very relevant. General studies, this is something generally that you don't find questions appearing from. So that is why even a basic information is more than sufficient. Okay. Now, here, let's suppose you have put a utensil and here you have filled it with water and you are putting it on a burner, on a stove. Now, let's suppose you have filled it with water. Now, initially, you won't observe any movement in that water immediately when you put it on stove. And you can try it today as well. I hope that you are not going to leave the session to try it right now. So try it after the session if you have never observed this. So basically, here what you will observe is, after some time, bubbles, they start forming at the base. Okay. Now these bubbles, they will start forming at the base, they will start forming at the base of the utensil, and slowly and steadily you will observe that these bubbles, they start to rise. Okay, they start to rise. Now when these bubbles rise, so what will happen here in this portion from where the bubbles have started rising? What is it that you observe here? So in this place, you will observe that there is a kind of a vacancy which is created, a kind of a vacant space which is created. So the colder waters which are present closer to the surface, because obviously when immediately you put water to boil, and if you feel the temperature at the surface, the temperature will be slightly colder, whereas at the bottom it will start heating up slowly and steadily. So the colder water which is on the surface, that is something which will start sinking down, and it will replace that vacancy, isn't it? So here you have a kind of a circulation of water, and via this circulation of water, what happens? Heat distribution takes place, isn't it? So by circulation of water, by circulation of water, heat is distributed across the material. Okay. Now, in the case of this circulation which happens, what happens? Heat is being supplied from the bottom, and the entire region basically helps distribute that heat because of the convection current. So this movement that you observe, where the warm liquid rises up and is displaced by the colder substrate or the colder material, this is what is referred to as a convection current. Now, this is also something that we will come across when we start talking about atmosphere, guys. That is again when we will be touching upon this. So this is what is your convection current. Okay, right? Now, Arthur Holmes basically said that something very similar happens in the region of mantle as well. Okay, so he suggested that this convection current is present in the mantle. Now, if I say that this same kind of a convection current is present or is to be found in the region of the mantle, then obviously the immediate question which shall follow is that where is the heat supplied from? Where are we getting the heat from? So we are basically getting the heat in the case of the mantle from where? From where do we get that heat? Very good. So it is from the core. So in most of the cases, that heat is provided from the region of outer core. So Arthur Holmes basically said that here, if I consider this to be the region of, let's say, the crust, right? And then I consider this mantle. Yes, now we can say that even in asthenosphere, that convection current is produced. But at the time when Arthur Holmes postulated this theory in the 1919 and 1920, he did not have a clue about asthenosphere, and our understanding with regards to asthenosphere was not there. So what he said was that heat is provided from the core. Okay, so in this case, heat is provided from the core. Okay, And which part of core? The outer core. Okay, so it is in the region of outer core. That heat is provided. Now, where is it and how is it that the outer core gets that heat from? We have discussed it in the second module, that why is it that the region of the core is still heated and why is it that it still has temperature. So where is it that the outer core gets that heat from? Beautiful, Pranay. And Rahul also, very good. Suguna, very good. Bhavna, Vaishnav, very good. So basically, we have seen at the time of formation of planet Earth that there has been a lot of heat which has been trapped in the interior since the time of the formation of the planet. Since the time of the formation, as the outer surface that started contracting and cooling and solidifying, the inner layers, they were still significantly hotter. So while the cooling exercise for the planet began from the surface to the interior, you still had significant amount of heat which was trapped in the interior. Now that heat which was trapped in the interior, that heat was referred to as the residual heat, right? So the heat in the region of outer core is a resultant of residual heat. Residual heat. Okay. Shikha, have you joined the session for Hindi medium or is it that you have joined for English medium? Please specify, because this session is for English medium. So that is why we won't be having the discussion in Hindi at all, right? I hope that is something which is very clear. And I hope no grievances are held that why it is not being discussed in Hindi, because obviously you have to write the examination. If you are attending the session, I'm sure you have to write this examination in Hindi, in English. So better to have the discussion in English itself, right? Okay, that is clear. So anybody who is making the demands with regards to that this language or that language, first of all, I'm not that proficient in so many languages out there. I do know 2 to 3 languages, but because you are going to appear there for the examination in English, let's have the discussion in English. Okay. Now, this residual heat, which was trapped in the interior since the time of formation, that residual heat is provided from the interior into the region of mantle. And that heat which is provided, what will it do? We know that what is the state of the mantle? Is mantle solid, liquid, or gaseous? What is the state in the case of mantle? Very good. It is solid. Some portion of asthenosphere is semi-solid or a semi-plasticky state. But in general, if you consider the entirety of the mantle, that mantle is solid, right? So here, this is mantle is in solid. Mantle, that is in solid. Now, here, when you have excessive heat which is provided, that excessive heat which is provided, now that heat, will it be distributed equally across the entirety of the planet or will it be concentrated in some areas? The answer is that heat which is trapped, from time to time, it gets released from certain portions of outer liquid core. For example, if you want to imagine it in a better way, think about this as the planet, right? Now think about the region as this being your region of outer core, let's suppose. So what actually does happen is that from time to time, you have that excessive amount of heat, let's suppose, which accumulates and is supplied from here. And it keeps on going on, and whereby the heat continues to be provided there, maybe for a few 100,000 years, or maybe for a few million years, maybe for a few 100 million years as well. And maybe after a few 100 million years, the heat from this portion that will be distributed, and then accumulated heat might start coming out from somewhere else. But at any point of time, you will not come across a situation where equally from all directions the heat is continuously supplied from the region of outer core. It is only in certain areas where that concentrated heating is supplied. Okay, so it is in this area where you have concentrated heat. Is supplied. Now, think about it one step at a time. Don't get ahead of yourself. Think about it one step at a time. Now, this is a solid layer. Now, in one portion of that solid, there is excessive heat which is provided. What will happen to that solid if that excessive heat is provided? What do you think? It will start melting, isn't it? So, basically, when it starts melting, here let's suppose you have a fluid or a liquidy layer in this particular portion. You will have that particular portion as liquid. Now, this liquid always is going to be lighter as compared to solid, isn't it? We know this much between solid and liquid. Generally, liquid tends to rise up as compared to solid, isn't it? Now, this liquid is superheated because there is continuous supply of residual heat in this region. So, this liquid is superheated. It will try to rise up, but then the material above it, that is still solid. So slowly and steadily, this heat will start melting the materials above it, and that heat starts traveling upwards. And when that heat starts traveling upwards, eventually, what will happen? It will reach the region around the crust or the lithosphere. Now, what is lithosphere? Again, we had talked about it in the second session itself. Lithosphere is basically the portion of crust plus upper mantle. That is the portion of lithosphere. Okay, so here, when we talk about it, so that portion of heat travels to the portion of lithosphere, and then that heat gets bifurcated. Just like in the case of this liquid, when we saw the convection current, how that heat gets bifurcated, and the colder materials, they replace the lower regions. So just like this, there's a kind of a movement here as well. Okay. Now, eventually, when that heat is supplied or is distributed, now after some time, the materials around which are colder, they will start replacing the portions which have been vacated. Okay, so they will start replacing the portion which has been vacated. So overall, you achieve what? You achieve again the existence of a convection current theory, or rather a convection current. Here also, you will observe the initiation of a convection current. Okay, so basically, Arthur Holmes, the theory that he postulated was that, look, just like in any liquid, when you heat a liquid, basically you have that heat which is distributed throughout the liquid by the movement of particles, and that is where you have the convection current which is generated on a similar level, on a similar scale. That convection current also does exist in the region of the mantle, and that convection current is also significant in terms of distribution of that trapped residual heat. And that is how the core is slowly and steadily losing heat from one end, and then after some time, maybe if it is losing heat for a few 100 million years, let's say from this point A, maybe after a few 100 million years, this point becomes slightly cooler, and another point, let's say B, that becomes significantly warmer or hotter, and they start rising from here. Maybe after a few 100 million years, even from B, that heat stops, and maybe the heat is then provided from here. So it is a kind of an unpredictable aspect with regards to where is it that this heat will be provided from. That is the aspect which is unpredictable. You don't know that where that excess heat is going to be provided from, but nonetheless, from the region of the outer core, that heat is continuously distributed in the region of the entirety of the mantle. Now here, Arthur Holmes was only talking about that distribution of heat, and he was talking about how that heat is getting distributed in the mantle. But you had a kind of a certain aspect or a context associated with it here. And that context or the aspect of it was that, look, wherever you have the vertical movement of heat, wherever in the region of lithosphere, let's consider this to be the region of lithosphere. So wherever you have in the lithosphere the vertical movement of heat which is provided, so suppose this is the lithosphere, if there is a vertical movement of heat which is provided, chances are that the land simply will get pushed up or will swell up in a way because of that heat, isn't it? And that would mean that land sometimes would rise up. Or if the land is weak enough, then those molten materials might break through the surface and even can lead to volcanic eruptions. So that is where you have the verticality of that heat which is provided, the vertical movement of heat which is provided. Now, it also meant that this heat, when it moves in a horizontal manner in these areas, in a horizontal manner, okay, thereby this heat will then basically, because it is moving horizontally, so what will it do to the region of lithosphere? Think about it. If this is the lithosphere, let's suppose the palm of my hand is a lithosphere, and there is that heat which is provided, and then it starts moving horizontally. So what will it do to the palm of my hand? What do you think will happen? Very good. It will get stretched, right? So here you would observe the stretching of the lithosphere. Now, if the lithosphere is getting stretched from both ends, what can we say with regards to its thickness? Let's suppose here. What can we say about the thickness of lithosphere in this place if it is getting stretched from both the sides? What do you think will happen? Beautiful. So this is something which will decrease the thickness of lithosphere. So the lithosphere will start getting thinner and thinner because it is getting stretched. So this lithosphere will start getting thinner and thinner. Now, when it is getting thinner, at the same time, you also have to understand that you also have the verticality of the heat. So the lithosphere is getting thinner, and you have the vertical movement of heat coming directly underneath the thin portion. So what will happen? There are chances, there is a probability that this thin lithosphere can easily crack, and you can have molten materials erupt from that portion, isn't it? Earlier, when the lithosphere was thick enough, maybe it could withstand that excess heat. But now that it is getting stretched, it is getting thinner and thinner. So thereby, that particular heat which is supplied, it can break through the surface. So that is when you have that vertical motion of heat vertical motion of heat can thereby lead to two cases or two impacts on the surface. One impact will be what? One impact will be, if suppose this is a lithosphere, because there is so much vertical heat, automatically the land will start to rise up. If this is, let's say, if let's assume this is the land, it will start to rise up ever so slightly. So that vertical movement of heat, vertical movement of heat, that is something which will give rise to what? It will give rise to two aspects. Either of the two aspects can happen. The land gets uplifted. And in many areas across the world, you will find or come across a scenario where this uplifted land, in a way, has led to the formation of plateaus in general. Or in many areas of the world, you will find that the land is flat for a long portion, but suddenly there is a kind of an uphill sort of portion. So that tells you that sometime in the past, this region would have experienced a vertical movement of heat from the interior. The second impact which can happen is that molten materials shall erupt through the surface in the form of what? In the form of volcanic eruption. Volcanic eruptions. Isn't it? These are the two effects. The direct effect that you can think about simple, by using simple logic, by using simple science, you can come at this derivation. Now, let us extend our concept a bit more. Now we talked about the fact that you have that horizontality of that heat as well. Just like verticality, you have that horizontality of the associated with the heat as well, where the heat is distributed in a horizontal manner. Now, when that happens, what will be the resultant? The land in itself will get stretched. The land in general can be pushed apart, right? Now, what happens in this portion? In these two areas, if you can look at these two areas on the sides. Now here, if you will observe, there is a sinking column. In a way, the heat distribution chart that you will observe even in this liquid, that you observe the distribution of heat. Here you have the sinking of the materials. So here also in the portion of mantle, you have the materials which will start sinking, isn't it? To replace the vacancy which is created. Now, because the materials are sinking in these areas, let's name these areas B and C. Okay. So here in B and C, you will have horizontality, and again in these regions, you will observe the materials that are sinking down. So if let's suppose this is the lithosphere, again apply your logic, let's consider this point C. So if this is the lithosphere, underneath it, the mantle is suddenly sinking down. Portions of the mantle are sinking down. What will happen to this surface? Will the surface lie as it is and the mantle will sink down, so there will be a vacuum created? Or will the land also start sinking along with the portion of the mantle? What do you think will happen? Beautiful. The land will also sink. So in these areas, the land or the lithosphere, that will start budging a slight amount. It will start budging or sinking ever so slightly. So basically, what the convection current theory indicates is the entire movement or distribution of heat which happens in the mantle, and that is how it can result in or lead to the various features or the movement on the land as well. Now, Arthur Holmes did not go further to talk about that whether this will lead to the continent formation or whether this will lead to an oceanic formation. He did not bother about that. He simply talked about how heat is distributed from the region of the interior to the region of the mantle. And basically, while doing so, he also alluded to the fact that in certain areas, you have the heat which is provided, which can push the land up or which can lead to volcanic eruptions. And in certain areas, it can lead to the sinking of the land because of the convection current which follows. So, this convection current which is present in the mantle can alter the shape of the surface in general. That is what the convection current theory is. Again, I will repeat, it does not talk about any aspect of, okay, this is how the continents are moving, this is how the continents have come into existence. No. It simply talked about how heat is distributed in the region of the mantle and what can be the impact of that distribution or the movement of heat. The vertical movement of heat can lead to the formation of a kind of an uphill or a volcanic eruption. The horizontal movement of heat in the mantle can lead to the stretching or the breaking of the land. And then again, you have the downward vertical motion, which can pull down the portions of the lithosphere as well. So that is where the convection current in the mantle influences the surface phenomena. Okay, this is all that Arthur Holmes had to say about this theory. Now, it was in the 1919 and 1920 era when our understanding about the interior of the planet was still very much restricted. It was still very much limited. We did not know much about the interior because remember, it was in 1912, somewhere around that time, when Alfred Wagner had basically borrowed the idea about the interior of the earth from Edward Suess. And remember how flawed that idea was. It was not at all perfect, it was not at all even accurate. So it was very, very flawed. Okay. Now, because it was very flawed, that meant what? That basically meant that you had the least understanding about the interior. So this, again, convection current theory did not try to go beyond its limits, but nonetheless, it did make a point, or it did contribute to the later theories by saying that this is how the surface can behave. Okay, I hope this is clear, right? Now, here, after this convection current theory was provided, which was provided in the 1920, now after that, for a couple of decades, there was a large lull or a silence in terms of geographical discoveries which were happening. Then, in 1939, you had the initiation of World War II. Now, during that World War II, obviously scientific discoveries, they do happen during an era of when you have wars and so on. Technological advancements, they do happen in certain areas. Now, during World War II, as you would have studied in your portion of world history as well, the Germans, they deployed a new machinery which was unknown to mankind till that point of time. And the Nazis basically deployed what they called as U-boats, or what today we call as the submarines, right? The submarines were one of the most potent weapons which were designed by the Nazi Germany, which could basically exist underwater, which could basically move underwater, making it very, very difficult to detect. And suddenly it would surface, it would attack a ship, attack any particular vessel, destroy that vessel, and again go underwater. So these submarines or these U-boats were creating a lot of havoc. Now, when they were creating this kind of havoc, so obviously countries such as United States, France, UK, etc., they started developing technologies to be able to detect these submarines. And that is when sonar, right, or a kind of an underwater radar system, that is something which was devised. Till that point of time, our understanding with regards to the bottom of the ocean was absolutely limited. when we took a look at the various oceans underneath which you had these submarines. So when we took a look at the surface of the surface of the ocean appears to be almost plain, almost very simple. So our understanding was that the base of the ocean would also be plain and simple and featureless. Nonetheless, during the era of the Second World War, there was a lot of this scientific discovery with regards to equipments which could detect things underwater. Now, the war ended in 1945. By that point of time, the Americans, the French, and the Britishers, they had developed such equipments. Now, when the war ended, what would they do with those equipments? They did not have to look for the submarines anymore. So what would they do with these equipments? So basically, these equipments were then utilized to study the ocean floor, because till that point of time, even this work had not been done. So that was used to study the portion of the ocean floor in general. Now, when you use these equipments to study the ocean floor, that is when a lot of information that started flooding in with regards to what the ocean floor looks like or consists of. Now, you had one of these naval expeditioners in America, that is Harry Hess. Now, Harry Hess again carried out this experiment in the region of the Pacific Ocean and some parts of Atlantic Ocean as well. And Harry Hess, when he observed these, he came upon a conclusion which was very stark and very significantly surprising. First of all, he came upon the conclusion that, look, the ocean floor that you guys keep talking about, that it can be plain, it can be featureless, that ocean floor is not at all featureless. It has got underwater mountains, it has got underwater ridges. Now, I hope we have some clue about what we mean by ridges. In case we don't have an idea about it, ridges basically refer to a kind of a phenomena which is like this, an upraised portion. This is what constitutes a ridge. So Harry Hess found out that underneath the ocean floor, you had a continuity in terms of the presence of these ridges as well. And these would be present along with underwater mountains. You had oceanic trenches. Now, what is a trench? So trenches, these are ocean deeps where suddenly, if you observe, let's suppose, if you consider this to be the ocean surface, if you consider this to be the ocean floor, then these will be your trenches. So he observed that you had the existence of trenches, you did have the existence of ridges, and he also basically studied the sedimentary deposits on the ocean floor by trying to figure out that how old these sedimentary deposits are. And based upon all this research, based upon all this understanding, he postulated what is referred to as the seafloor spreading theory. So this is basically the seafloor spreading which is provided by Harry Hess. Harry Hess. Now, Harry Hess postulated this theory way back in around 1953. After conducting the studies on the ocean floor in the case of the Pacific and the region of the Atlantic, that is when he studied the ocean floor. He studied the deposits that you would find in the case of the ocean floor, and then he postulated the seafloor spreading theory. Now, what is this seafloor spreading theory that was postulated by Harry Hess? So, first of all, let us understand a basic glimpse of what this theory talks about, and then we will talk about the fact that what this theory tells us, whether this theory is correct or incorrect, and why, and so on. So Harry has said that, look, underneath the region of the ocean floor, you have the presence of this mantle, and in that mantle you have areas where that vertical heat is provided. So in those areas where that vertical heat is provided, you have materials which can crack from underneath the ocean floor. and it can break into volcanic eruptions. Now, why only underneath the ocean floor? Why not underneath the continents? Because the oceanic crust we have seen is much thinner, having an average thickness of around 5 to 10 kilometers, whereas the continental crust, they are significantly much more thicker, right? So he said that, look, there is a creation of volcanic eruption underneath the sea floor, in the region of the sea floor, due to the vertical movement of heat. And that heat which is provided eventually leads to expulsion of materials, and those molten materials, they will then solidify to form the newer crust. In this process, as they form the newer crust, the older crust is being pushed aside. So in a way, as this newer crust gets created, the older crust not only gets pushed aside, but then here, this older crust, when it is pushed aside, what will happen to the area of the sea, the area of the water body? If let's suppose this is the water body, this is the floor. Now, here, let's suppose newer crust is getting created. So the older crust, that is getting pushed aside. So what will happen to the area of the water body? Water body will expand, isn't it? The oceans or the seas, they will start to get larger and larger. So that is what is referred to as the spreading of the sea floor, or what he propounded as the sea floor spreading theory. So as per this sea floor spreading theory, we'll talk about the nuances of it as well. That talks about the fact that underneath these oceans and the seas, you have the presence of certain mid-oceanic ridges. Mid-oceanic, why? Because they are found into the deeps of the oceans. So these ridges, basically, they resemble a kind of an uphill portion, right? This is what we refer to as ridges. Okay, they resemble, this is what we refer to as ridges. So he said that along these ridges, you have the creation of a newer crust, while the older crust gets pushed aside. Now, please understand here that this is something which is very similar on the lines of what Arthur Holmes had said. That Arthur Holmes had said that because of the convection current which exists in the interior of the mantle, there is that vertical motion of the convection current, there is that horizontal movement of the convection current, and eventually there is again that vertical motion of the convection current. That is what Arthur Holmes had propounded. Now, basically, the seafloor spreading theory also relied upon these aspects. It relied upon the aspect that, look, this horizontal movement of heat is the one which can also be responsible for pushing the older crust aside, away from each other. And eventually, the sinking portion of that heat, that sinking portion of heat eventually is the one which is going to pull that lithosphere slightly downwards. And when it pulls the lithosphere slightly downwards, that is when it creates a phenomena which is similar to that of an oceanic trench. So, in a nutshell, he's basically talked about the oceanic crust or Earth's crust and how that Earth crust behaves. He said that the newer crust gets created at the region of the mid-oceanic ridges, while the older crust, in the case of the oceans, they basically are subsumed in the region of the mantle. They are basically consumed in the region of the mantle because of that kind of a convection current. And it is in these regions of oceanic trenches where the older crust is consumed. That is what he said. Now, here, all that he said was based upon certain observations that Harry Hess had basically conducted. So if you take a look at the observations that Harry Hess had made, so amongst that observations, he had basically said that, see, oceans are not featureless plains. That was the first discovery that he made, that it is not a featureless plains. It consists of various features like mid-oceanic ridges, rise which is present, oceanic continental rise, as we will study in the portion of oceanography, trenches, abyssal plains, or the deep sea plains as they are referred to, deep sea plains, and also sea mounts. Sea mounts refer to underwater mountains. So, the seafloor is consisting of all these portions. Plains are basically the flat regions. Okay, plain means what? Something which is flat. You say that the table is plane surface. Okay, so this is basic English. So deep sea plain means the flat region at the end of the sea. So here, that is what he observed. Then he observed that oceanic rocks that he came across, all these oceanic rocks, they are significantly younger as compared to the rocks that you find on the continents. He basically observed this in the case of certain areas where he observed that regardless of whichever oceanic rock that a person picks up, that oceanic rock is not older than 200 million years. And the oldest one that he found in the case of the Atlantic was only around 200 million years old. Whereas in many areas across the continents, for example, in the region of Australia, you find the evidences that certain rocks, they are as old as 3 billion years. So he said that oceanic rock sample in terms of age were nowhere more than 200 million years old. And continental rocks are way older than the oceanic rocks, and some continental rock formations are as old as even 3.2 billion years. 3.2 billion years. Okay, 3.2 billion years is where you have the age of certain continental rocks, whereas the oceanic rocks, they are much younger. That means what? That means that the crust in the case of the ocean bottom, that crust is getting created at a rate which is faster, or is getting created at a much later time as compared to the continental crust. Now, he also observed that near the mid-oceanic ridges, wherever you talk about the mid-oceanic ridges, so for example, let's assume this is a kind of a mid-oceanic ridge. Okay, so this is your mid-oceanic ridge. So he observed that the rocks which you will find immediately close to the mid-oceanic ridge, these rocks are much younger. Younger rocks and younger deposits. Okay, so here you have the presence of younger rocks and younger deposits. Whereas as you move away from mid-oceanic ridge, here, as you move away from mid-oceanic ridge, there you will find the presence of older rocks. Okay, now this was one of the observations that he made. Then basically rock samples were younger, and near the oceanic trenches, the rocks are the oldest, but even there they are less than the 200 million years. What is an oceanic trench? ocean. What is a trench, by the way? How many of us, we don't know the English meaning of trench? Don't worry, I won't take your name at all. But how many of us, we don't have any clue what is the meaning of a trench? World War One oftentimes is referred to as the trench warfare, right? Have you heard about that? That World War One is referred to as the trench warfare? Okay. No. Okay. So when we talk about an oceanic trench, think about it. So suppose if you think about it that this is the ocean surface. Now, at the ocean bottom, if you will consider. Now, by the way, the average depth of ocean bottom in general in the major oceans that you will find is around 3 to 6 kilometers. That is how deep the ocean floor is. However, in certain areas, you do have the presence of a further deeper kind of a section, which is very, very narrow, right? And this is what is referred to as an oceanic trench. Example, you have Mariana Trench, which is the deepest trench out there in the world. Mariana Trench, then Coral Trench, then you have the aspect of, yes, Sunda Trench, then after that, Tonga Trench. So you have many such trenches which are present at the ocean bottom. So basically, you observe that near the oceanic trenches, the sedimentary rocks or the deposits that you will find in the rocks, they are significantly older as compared to the portions that you consider closer to the mid-oceanic ridges. So on the crest of the mid-oceanic ridges, cracks with continuous active volcanic eruption, they were also found. Okay, so at the crest of these mid-oceanic ridges, you had cracks. So for example, if let's suppose here I have a mid-oceanic ridge. So here he observed that there were cracks, and from these cracks you had the volcanic eruption which would occur, volcanic material which would emerge underneath the water and it would spread. Okay, that is what he basically observed. Now, age of rocks and types may be similar for any two places equidistant from either side of the mid-oceanic mid-oceanic ridge. Meaning what? Meaning that basically when you talk about it, so for example, here, let's suppose this is the mid-oceanic ridge. Mid-oceanic ridge. So basically, if suppose I measure the age of the rocks which are equidistant from the ridge, that basically tells us that it is equidistant, and when they are equidistant, they will have same age. They will have the same age of the rocks as well. So here, this is basically the observations that Harry Hess had conducted, or he had basically concluded. Now, based upon these observations, let us understand what this seafloor spreading theory is. So he said that, look, or he observed that, look, there is a mid-oceanic ridge underneath the water where you will find active volcanic eruption happening. Okay, so underneath this, across this mid-oceanic ridges, here you will find active volcanic activity. He also observed that as you move away from that mid-oceanic ridge, the rocks will indicate to you that immediately closer to the mid-oceanic ridge, you will have younger rocks. And if they are equidistant from the mid-oceanic ridge, that would indicate that these rocks have the same age. And then as you move away from the mid-oceanic ridge, closer to the oceanic trenches, that is where you will find the older rocks which are present, but that too is nowhere old as compared to, or nowhere older than 200 million years. So that is where he basically propounded a theory that, look, there is volcanism which happens underneath that oceanic water, which leads to the spread of the sea floor. How can the spread of sea floor happen? By creation of a newer crust. So newer crust keeps on getting created time and time again, while the older crust is continuously pushed aside. And that older crust in the ocean is then consumed at the oceanic trenches, where they are dragged down because of the verticality or the vertical movement. And that is where eventually the entire circulation of the oceanic crust takes place. That is why you don't find the presence of newer crust in the, or that is why you will find that oceanic crust is much younger. Okay, so here, if you talk about it, basically, here the theory, the theory. What does the theory tell us? First of all, ocean floor is not featureless, and is dotted with various landforms like mid-oceanic ridge, trenches, seamounts, etc. Then ocean floor, or the presence of newer crust, indicate the formation of crust at mid-oceanic ridge due to what? Due to signs of active volcanism. Then, as the newer crust is created, the older crust basically pushed aside. Older crust is pushed aside, and that is where leads to expansion of sea floor. Right, which is also referred to as sea floor spreading. Okay, that is what is sea floor spreading. Now, the older crust, or rather, this spread of sea floor leads to the existing continents being pushed aside. That is, away from each other. Okay, now the older crust that is oceanic crust. He only talked about oceanic crust. He did not talk anything about continental crust at all. So the older oceanic crust sinks at oceanic trenches leading to a circulation. And he propounded that it is because of this circulation that you will come across a situation that oceanic crust is much younger. Whereas such kind of circulation you don't observe in the case of the continents, and that is why continental rocks are much older, whereas the oceanic ones, they are much younger. That is what he propounded. That is what he basically said. Now, how is it that newer crust gets created? It is okay to understand that yes, there is a volcanic eruption which happens, but how is it that newer crust will get created? Let us think and understand about that in a very simple terms. It is a very simple thing to think about it. So suppose I consider this to be a mid-oceanic ridge region which has got the presence of the crust. Moina, have you understood the point till now? All those who have not understood the points till now, and you are straight away talking about paleomagnetism, right? First of all, paleomagnetism is not a part of seafloor spreading theory. Please get that very clear, right? Just because you have seen somewhere paleomagnetism and so on, and you are asking about it, first of all, get this concept clear. This is what many of you get incorrect. This is where many of you, and please take it as a word of advice if you can, many of you will commit these mistakes that I have heard about tropical cyclones. So rather than looking at atmosphere and everything, just tell me tropical cyclones so that that kind of curiosity is quenched, because I had seen one question from tropical cyclones. Unless and until you don't understand the portion of seafloor spreading, there is no point understanding about paleomagnetism. Paleomagnetism and the entire concept of paleomagnetism came 10 years later than seafloor spreading. That is where many of the books also give you the wrong information. So I will cover all of this, okay? But first of all, please pay attention to what is being taught, because what will happen invariably is when I get to paleomagnetism, then Because the previous concept is not clear, you will ask, but how is it that the seafloor is getting created like this? Why is it that near mid-oceanic regions we have this kind of a magnetic anomaly? So we will go there chronologically. Okay, have this much amount of trust. Okay. Now, here, let's suppose this is the oceanic crust. Oceanic crust. And this I'm talking about how is it that the creation of newer crust takes place. That is this point that we have talked about, that newer crust is created, the older crust is getting pushed aside. How does that happen? So basically, here, let's suppose there is this convection current and that heat which is provided. Now the molten materials, they will try to rise up. They will try to rise closer to the surface, isn't it? Now, when they start rising up and come closer to the surface, what will happen? There will be a volcanic eruption. And that volcanic eruption eventually will lead to the solidification of materials. And those solidification of materials, you will find that you have the materials, newer materials, which have been solidified. At the same time, convection current theory also tells us that there is a horizontal component of that heat which is provided in the region of the mantle. So that means at the same time, this oceanic crust is getting pulled away from each other. Now, when this oceanic crust is getting pulled away from each other, what do you think will happen here? In the portion where things had got solidified due to a volcanic eruption, what do you think will happen to that portion which is joined, which has been formed recently? What do you think will happen? As it is pushed or pulled aside, there will be development of a newer crack. Very good. There will be a break in this and it will lead to the creation of a newer crack. So here, when you talk about it, after some time, the oceanic crust will look like this. It has broken. And the earlier ones, which was the crust which was created, that will also get broken. Okay, so basically, this is where the crust is breaking. Now, this portion of vertical rise of heat that continues. Now, as this vertical rise of heat continues, what will happen next? You will have more molten materials which will come here. So more molten materials will fill the gap. And what has happened? Again, you will observe creation of a newer crust, isn't it? And when this newer crust is created, means what? The earlier one which was present, that has now been pushed slightly aside, right? And again, if you measure the distance from that mid-oceanic ridge, both these areas will give you an information that, okay, these are equidistant from the mid-oceanic ridge as well, isn't it? Now here, again, there is that horizontal aspect of heat as well. Horizontal aspect of that heat movement as well. Now, when that horizontal movement of heat comes in, that also means that there is another aspect of pull, and which would lead to what? Again, a breakage in the crust. Again, when the crust breaks, then what will happen? Then, basically, you will come across a situation where the crust has again broken and the older ones, they are continuously being pushed aside. The older ones which were present, which were created, they are the ones which are getting pushed aside. Now, what will happen again in this gap? In this gap again, materials will solidify. So again, you will have what? The formation of newer crust. Formation of newer crust. So this is how, when you have newer crust which keeps on getting created, think about it, apply your logic slightly if you can spare some logic here, apply some logic. So suppose I consider 2 points A and B. Now, after some time, this A and B will be where? Here and here. After some time, this A and B will be where? Here and here. So what does that tell us about the oceanic crust? It tells us, or the sea floor, it tells us that the sea floor is spreading. It is increasing in size. Now, again, use your imagination a bit. Suppose I have one continent here and I have another continent here. Now, if this is the sea in between them, and if this sea floor in itself is spreading, can I not say that as a result of that spread of the sea floor, the continents, the existing continents, they will also be pushed aside? Because there is a creation of a newer crust, the sea floor will start spreading. So that is why the existing continents, they will start to be pushed aside. By this, Harry Hess could very well explain why is it that in the region of Atlantic, you don't find the presence of rocks which are older than 200 million years. Now, why in the case of Atlantic? Now, I will take you back to the portion of the evidence of continental drift theory. When we were talking about the continental drift theory, remember the geological evidences which were used by Alfred Wegener. Now, Wegener had used an evidence based upon the fact that the region of the Appalachian Mountains in United States and the Scottish Highlands, they were created at the same time. The region in the eastern portion of Brazilian highlands and the region in Western Africa, they were created at the same time. So basically, the understanding was that at one point of time in the past, there would not have been any Atlantic Ocean. North America would have been joined with Europe, and that is where the two portions would have been created at once. That is the Appalachians and Scottish Highlands. And again, because you would have had the condition of South America and Africa joined together, that is where you would have had the creation of both the rocks at once. So this seafloor spreading talked about the fact that you have the expansion and creation of that Atlantic Ocean, and that has happened recently. That is why in the case of the Atlantic, you don't find any rock sample which is older than 200 million years old, because that has been created only around 200 to 250 million years back. That is when the Atlantic has come into existence. Right? So that is the aspect of the seafloor spreading. Okay? Now, Amit, sir, you written older crust is sinks, but now you are saying pushed aside. Hmm. So, Amit, first it will be pushed aside, then it will sink. Remember the portion that we talked here? First it is pushed aside, and then it is sinking. Right? So the older crust, first it will be pushed aside, it will sink. Will it be the situation that the older crust here itself, will it start sinking? Will the older crust start sinking here itself? Absolutely not. Right? So I hope this portion is clear. Now, Preetham, seafloor spreading. Seafloor spread, seafloor spreading is, okay, this is the theory. Do you want me to repeat the entire theory? That is not going to happen. Yes, Yuvraj, that is a correct assumption to make. So basically, that is the aspect which was provided by Harry Hess. He said that, look, in the case of the ocean floor, okay, Pritam, listen to this carefully for the last time, okay, because I've repeated this again and again in multiple different ways and directions at least thrice. So listen to it for the last time. So seafloor spreading theory basically talks about that the floor of the ocean or the seafloor, that is where it is expanding. And as it is expanding, it is pushing the continents aside. Now, why will it expand? How will it expand? It will expand due to volcanic eruptions which happen at the mid-oceanic ridges. And at those mid-oceanic ridges, when there is more volcanic eruption which happens, that leads to the creation of a newer crust in that region. When that newer crust gets created, as a result of that, the older crust is pushed aside. And slowly and steadily, the older crust that is not only pushed aside, but eventually it is consumed in the form of oceanic trenches. Okay, so that is something which was talked about by Harry Hess. And Harry Hess talked about this entire theory based upon the set of observations that he had made with regards to what the oceanic floor looks like, what the oceanic crust looks like, what is the age of the rocks closer to the mid-oceanic ridge, why is it that there is volcanic eruption at the region of mid-oceanic ridge. Based upon those aspects, he had postulated this theory. Okay, so basically, if you have to simplify it, if you have to think about it, so think about it in an aspect where, if let's say this is the seafloor or the surface, and here, if this is the seafloor, let's suppose this is the seafloor. So this is your mid-oceanic ridge. So here you have the creation of a newer crust, due to which the older crust will be pushed aside, and eventually at the continent ocean margin, that is where, in the case of the trenches, the older crust is consumed. Okay, at the region of these trenches, the older crust is consumed. Is consumed. Yes, Yuvraj. Okay, this was the theory. This theory is not picture perfect, by the way. So all of you who are getting restless and wondering that why is it saying like this is not the reality. This theory was not picture perfect. Basically, Harry Hess had made certain other assumptions as well. And certain other assumptions that he made, he could not fructify those assumptions. He could not carry out the research to that assumption significantly. But all these significantly helped us to understand. Now, by this theory, he could very well explain why the region of North America and South America, they are moving away from Europe and Africa. Isn't it something which Alfred Wagner could not do? Alfred Wagner could never explain that why is it that the continents are drifting away from each other. But by this, Harry Hess could explain that why is it that the continents are moving away? It is because the sea underneath them, that is expanding. And basically, he went a step further. He went a step further to basically suggest that this region that you observe, that is the region of Atlantic, this has been created at the region of the mid-oceanic ridge, and this is where the sea floor is spreading all across. Okay, so that is why we observe that North America is moving away from Europe and South America is moving away from Africa. At the same time, you have the contraction of the Pacific, which is happening because obviously North America is moving into the Pacific. So there is a kind of a contraction which is happening in the region of the Pacific. Okay. So that is something which he had propounded. Now, his theory also had certain limitations. So what were the limitations of his theory? So one limitation was it does not explain the small features of the ocean floor. For example, his theory does not, now he had made this observation that oceans are not featureless plains, but he did not talk about why is it that the ocean floor has got the existence of, let's say, the sea mounts or underwater mountains. He did not talk about the presence of other oceanic features which are present on the sea floor. Now, this theory does not talk about the movement of the continents per se by what is happening underneath the continents, right? For example, did not mention what is happening underneath the continents. Now, in the entire concept of that seafloor spreading, Harry Hess had only talked about the aspect of the crust. He did not mention the aspect of the lithosphere as well, right? So he only talked about the aspect of the crust. Lithosphere is the one which moves. Now we know that. So now we can criticize that. At that point of time, we did not know that. Now, this is again one of the drawbacks. Now, another drawback is, if you look at the basic crux, if someone asks you to simplify the entire theory in one sentence, the entire theory can be simplified in the manner that newer crust gets created at the mid-oceanic ridge and the older crust is getting consumed at the oceanic trenches, isn't it? Now, all the while the newer crust is created, that means there should be so many trenches as well. As you compare the mid-oceanic ridges, you should have the similar number of oceanic trenches as well. So that would mean that in each and every ocean, closer to the mid-oceanic ridge, you should have the oceanic trench. But that is not the case. It is not as if everywhere where there's a mid-oceanic ridge, there is an oceanic trench. That is simply not the case. That is simply not the situation. So here, it does not, the theory talks about the oceanic trenches consuming the older crust. Okay, the theory talks about, so that would mean the older crust or the oceans would necessarily have a trench close to a mid-oceanic ridge. Only then can the entire circulation happen. If at one point it is being consumed and other point it is being produced, only then the circulation can happen. Can it happen that newer crust is getting created, but it is not getting consumed? Can that happen? No, because the surface area of the planet Earth is fixed. It is not as if Earth in itself is expanding in size because of the creation of a newer crust. So that means for every mid-oceanic ridge, there needs to be a trench in presence. But that is not the case, right? So that is again a limitation about this theory, which was not provided by Harry Hess. So here, but the newer, but the oceans do not, or rather, let's have, but all the oceans do not have the trenches. Okay, so these were certain limitations. Shivam, basically, he did not say what is happening underneath the continents. Why is it that the continents will be moving? He did not say that, right? So it is something that we postulate, we derive at, but this is not something that Harry has directly talked about. So that is basically what is the aspect of the limitations of his theory. Now, then these are your mid-oceanic ridges across the globe. So this is your mid-oceanic ridges. Oceanic ridge. Okay. Now here, all these that you see in bright blue color, all these areas that you see in bright blue color, these are all your mid-oceanic ridges which are present. So the sea floor along the active mid-oceanic ridges, the sea floor is actually expanding. Okay, that is what he talked about. But then obviously, this was not a perfect theory, so to say. It had its lacuna, it had its drawback, but nonetheless, it gave us some information that, okay, this is something which is happening underneath the ocean floor because of active volcanism. And maybe that is why the region of North America, South America, they are moving away from Europe and Africa. And that significantly sparked up that curiosity in the minds of many of the geographers, and thereby that led to the postulation of newer theories as well. So overall, this is observed by Harry Hess, an American geologist. It corroborated the fact that the continents indeed they drew drift, and basically that formed the basis of the plate tectonic theory. Now, another aspect of it. Now, when you had Harry Hess talk about studying the region of mid-oceanic ridge and studying the ocean floor, he basically conducted a study in the sense that he looked at the ocean floor and studied the age. Now, how do you study the age of the ocean floor? So for that, you study the magnetic field. So suppose this is your ocean floor. Suppose this is your ocean floor. Let's suppose. Now, let's suppose this is your region of mid-oceanic ridge. Now, Harry Hess, he used the magnetic properties and studying the magnetic properties, the magnetic alignment of the rocks in order to calculate the age. What is this? The entire property. That is something which is referred to as paleomagnetism. Paleo means study of something which is old, right? So that is what is paleomagnetism, whereby you are able to calculate the age of the rocks based upon the magnetic properties. Now, how is it that it is going to help us understand the age of the rocks? For example, suppose if you consider the planet We do know that the planet has got a magnetic field around it, and that magnetic field keeps on changing with time. Now, in any place, let's suppose here, if I consider the planet, if I consider this to be the planet. Now, the magnetic field keeps on changing time and time again. Now, here, if there is a creation of a newer crust means, let's suppose here you have a creation of a newer crust. Now, newer crust means molten materials will solidify in that region, isn't it? Now, molten materials, they will have various different minerals. They will be influenced by the Earth's magnetic field and its directions. So, let's suppose the direction of the magnetic field is in this angle at a point of time when this was created. So, this particular rock which will be created will have a magnetic alignment somewhat like this. Okay. Now, over a period of time, let's suppose that magnetic alignment has changed. That magnetic alignment has become somewhat like this. And another rock which gets created at a later stage, let's suppose here. So the liquid materials, before they start solidifying, they will align themselves based upon the present magnetic field. So like that, when you take a look at the magnetic field or the magnetic field line arrangement within the rocks, you will be able to calculate how old it is. How? Because with the help of computer simulations now, by looking at how the magnetic field of the planet is changing continuously, we are able to predict that what the magnetic field line would have been maybe 3 million years back or even maybe 300 million years back. So that kind of a simulation is available to us. So when we take a look at the magnetic field arrangement present in a rock, we match it with the computer simulation and we get an idea about how old that particular rock is. So there, when he studied the region around the Pacific, he observed something very unique. He observed basically the fact, first of all, he expected that there will be a similarity in terms of the magnetic properties that the rocks are indicating, but that was not so. The rocks were indicating a very significantly different magnetic field lines. Right. Now, here, the magnetic field lines that the rocks were indicating were different. Let's suppose they had a different magnetic field line closer to the mid-oceanic ridge. Then let's suppose the other one had another magnetic field line which was indicated. Then let's suppose another one had another magnetic field line. Then let's suppose another one had another magnetic field line. And let's suppose that was followed by another one. Now he expected the magnetic field line to be uniform, but he was surprised by it that the magnetic field line is changing closer to the mid-oceanic ridge. But then he was further surprised when he mapped these magnetic field lines on the other side of the mid-oceanic ridge. There he found something which was very stark, which was very, very significantly similar to the other side. So he observed basically that if you consider, let's say, 2, 4, right? So he observed that if you observe or measure the magnetic field line on the other side of the mid-oceanic ridge, they show a stark similarity in terms of the magnetic alignment that the rocks indicate. Now, what does that signify? If you are equidistant from the mid-oceanic ridge, the rocks indicate the similar magnetic lines of arrangement. That means those particular rocks would have been created at the same time and then would have been virtually pushed aside. Right? So this indicates similarity of magnetic field lines of the rocks which are equidistant from the mid-oceanic ridge. And when you have a similarity of magnetic field lines equidistant from the ridge, that basically means what? The rocks would have been formed at the same time and hence indicate a similarity of field lines. Now let me repeat the entire concept once. All of those who are slightly fidgety with this concept, let me repeat the entire concept once. So basically, when Harry Hess was conducting his research on the seafloor off the coast of California, that is the western coast of United States, he started observing and measuring the magnetic field lines across both sides of the mid-oceanic ridge. Now he mapped out the magnetic field lines indicated or exhibited by the rocks. Now, in case you are not able to imagine what is this magnetic field lines of the rocks, so listen to this carefully. We have already talked about the fact that planet Earth has got magnetic lines of force, magnetic field around it. Now, why is that magnetic field exerted or is present? That is also where we had discussed that it is because of the liquid outer core which rotates continuously. That is why you have the magnetic field lines which are generated. We had also discussed the fact that that liquid outer core basically is not of uniform distribution. Sometimes some areas will get more amount of iron nickel, some areas will get more, and it keeps on changing. As a result of that, over a period of 4.5 billion years since the formation of the planet, the magnetic field lines have changed thousands of times as the concentration of iron and nickel in the outer core that undergoes even a slightest of change due to the rotation, magnetic field lines can change. For example, in the year 2020, around the month of April and March, there was a lot of news story revolving around the fact that the magnetic pole has shifted in the north from the region of Alaska to the region of Siberia. So that is where the magnetic field lines have always been changing. Now let's suppose today, let's assume today. Now today is 14th of March 2023. Let's suppose somewhere there is a volcanic eruption which is happening. Let's assume volcanic eruption is happening somewhere in Indian Ocean. Now that volcanic eruption which is happening means what? That molten materials are brought to the surface. Those molten materials will solidify. Now those molten materials will have ions, electrons, etc. Now they will align themselves based upon the magnetic field line which is present today. Now let's suppose we consider 500 years into the future. Now at that point of time, let's suppose the magnetic field line has changed. So if a rock is getting created at that point of time, the solidified rock will indicate the magnetic realities 500 years down the line. So someone down into the future, ahead in the future, if they are studying the rocks, they will be able to distinguish that, okay, this is a rock which indicates a magnetic field line which would have existed in 2023, and this is a rock which indicates the magnetic field line which would have existed in 2523, 500 years down the line. So by studying these magnetic field lines, you are able to understand, you are able to presume, you are able to get the age of the rocks. And that is something which is referred to as paleomagnetism. In simple terms, paleomagnetism is a study of the age of the rocks based upon the magnetic properties that the rocks indicate, which is more or less an attribute of the rocks at the time of formation itself, when they are solidifying at that time itself. So that is the aspect of paleomagnetism. This entire aspect of paleomagnetism was developed 10 years after the seafloor spreading came through. And basically, in this paleomagnetism, if you will observe around the region of mid-oceanic ridge, initially you will observe that there is no uniformity in terms of magnetic field lines if you consider one side of the oceanic crust which lies on the mid-oceanic ridge. But as soon as you match it up from both sides, there is a significant amount of similarity which exists, isn't it? So that tells you that if two areas have a similar magnetic field line, that indicates that they have been created or formed at the same point of time, indicating that as you move away from, or as you are equidistant away from mid-oceanic ridge, there is a same time scale for its formation. Okay, so that is the aspect of paleomagnetism and the seafloor spreading theory. Okay. How to study magnetic poles? Pritham, that is generally studied with the help of your general compass, my dear friend. We all know that the compass points to the north, right? And that is a very rudimentary compass that we have. Now, here, that if you have a developed and a more accurate compass, it will tell you the exact latitude and longitude in which it is pointing. Now, that in itself keeps on changing with respect to the rotation of the planet over a period of hundreds and thousands of years. We have been able to fit that into the portion of the computer simulation, and we are able to now calculate what the magnetic field line would have been 15 million years ago, 15,000 years ago, or maybe 1500 years ago. So if you come across a rock which indicates a magnetic alignment, let's say A, you fit that A data into the computer will tell you that, okay, the age of this rock is around 50,000 years ago. So you get an idea about the age of the rocks. Okay. Right. And okay, Sarthak, you are asking this question that liquid core of liquid core of core is upward up to lithosphere. Sarthak, please read the question that you have put. Liquid core of core is upward to lithosphere. What is the meaning of that, my dear friend? I'm not so good in English. Kindly specify that, simplify that for me. Okay. What is the, Sachin, what the sea spreading actually means? Is it causes the change in the ocean surface or the change in the earth movement? Because we know that earth is not floating on. Okay, fair enough. So basically, Sachin, what you are trying to ask is that what is this seafloor spreading talking about, that the ocean floor is spreading away from each other, because not everything is floating. So how is it that they can expand? That is where the convection current theory comes into place, my dear friend. That convection current, the verticality, the horizontality of the heat, that is something which will pull the crust, that is something which will pull down the portion, and that is where the circulation will happen. Limitation, the third limitation of the seafloor spreading theory, Devansh, the seafloor spreading theory did not talk only about the crust. It did not talk about the lithosphere. In actuality, the movement is observed in lithosphere rather than only the crust. Okay. Anil, the concept of Atlantic is 200 million reasons. Atlantic is 200 million reasons. Okay, 200 million years old you have forgotten, and you have simply written 200 million. Okay, the aspect of that is that because you don't find any sediment or any rock in the Atlantic which is older than 200 million years, what does that tell you? That there would not have been the presence of that seafloor 200 million years back. That is why all the deposits are only as recent as 200 million years, isn't it? Now, if Atlantic would not have existed 200 million years ago, because there are no rocks which indicate that age, what would have been present? That means the continents would have been together. Okay. Paleo means something which is very old. Paleontologists, right? The study made by paleontologists. We studied in the continental drift theory. Paleontologists are the ones who study the ancient fossils, the fossils of dinosaurs, and so on. So that is something, study of something which is old and ancient. Okay? Absolutely, yes, Anil. As you talked about the fourth limitation, the ridges are not created. No, fourth limitation, Yashika, is that not in every ocean will you find the presence of ridge and trench as well. You will have certain oceans where only there is a ridge, there is no trench. So in a way, that is something which is falsifying his theory that newer crust will get created, older crust will get destroyed in every ocean. But that is not the case. Okay. Kausar, absolutely not. What is observed in Joshimath is something very, very different from what we are studying here. Joshimath is a very localized phenomena. We have put YouTube shorts on that. Kindly look at that. Okay. Sarthak, we will talk about it. All of you, we will talk about volcanoes, we'll talk about earthquakes. The doubts that you have up till now, please ask those doubts. Please don't ask the doubts that you have in your life. The doubts that you have till now, which has been covered till now, ask that. That is something which will be more relevant. If I have a doubt that why the sugar prices are going high, I cannot ask the doubt right now. We'll come to all of this. Okay? Right. So basically, this theory, the seafloor spreading theory, this was the first comprehensive theory to talk about the movement and formation of newer crust in the sea floors. Now, simultaneously, other scholars such as Mackenzie and Parker and Morgan in 1960s, okay, 1960s, they developed a more comprehensive understanding of the movement of different part of the earth crust, both oceanic and continental, and the related formation is explained under the theory of plate tectonics. So all the learnings that we have gained from the portion of continental drift, from the portion of seafloor spreading, from the portion of convection current, all of that now will lead us into the theory of plate tectonics. Now we'll come to plate tectonics. Before that, we'll take a break. NCRT related doubts. Moina, which NCRT related doubts are we talking about? 11th and 12th NCRT you can study if you have a doubt with this. Now, please understand, not all the information that you are getting in the class, not all the information will be present in the NCRT or the book. So please don't start having a grievance of that, that what you are teaching is not present in the book. What is the benefit of attending the class if it is? So we are covering portions from many different books. You will get a basic reference from the NCRTs of 11th and 12th. Okay. Yuvraj, Harry Hess provided a theory which is referred to as seafloor spreading theory. Okay. So now we take a break, and we take a break. I think you need 15 minutes. So let's take a break of 15 minutes. We'll be back by around 7:10. Okay. Right. Atlantis, I was really wondering that till now nobody has mentioned Atlantis, because yesterday someone had mentioned about Lemuria. So it was high time that someone mentioned about the myth of Atlantis as well. No, Atlantis, let it remain in the mystery books. Let us not consider. And all those who are curious enough for Bermuda Triangle, about alien life, about lost city of Atlantis, about the lost supercontinent of Lemuria, all those conspiracy theories that you are curious about, this is not the platform to talk about it. Let's meet over a cup of coffee sometime and we'll have a long discussion over it, but not this platform. Okay. Devansh asked this question at the end. Remind me at the end, and I will talk about the aspect for males. Okay, let's take a break, guys. Take a break, splash some water on your face. We come back, we study the plate tectonic theory, and we move ahead. A confirmation regarding the audio, please, guys, if you're able to hear me out perfectly well. Thank you. Um, is it necessary for everyone to read NCERT because lecture and notes are easily understanding? See, if you are able to understand everything that we have been talking till now, fair enough. Revise it as much as possible. Still, I would want you that before the examination, that let's say you are appearing for the 2024 examination, I would want you that in the month of December, just flip through the NCERTs once. If you are regular and if you are able to understand and follow the entire portion of the lecture very easily, then those NCERTs you will be able to complete maybe within a week. But once you are able to do that, what it will do is it will provide you with that necessary boost of confidence. Prelims is a lot about the confidence that you carry to the examination hall. And many of the times when you don't refer to the books, you do lack some amount of that confidence. So for that purpose, I want you to flip through it. Otherwise, there is not much of a significant information that you will get from the NCERTs which you don't have in the lecture. Okay. As of now, if you are preparing for an examination beyond 2024, I would suggest to you follow this lecture very significantly along with the additional reading materials. Try to reinforce the concepts as much as possible so that by next year, your entire general studies should be completed. Year after that, devote it for the portion of optional. Meanwhile, start working on your current affairs. So those of you who are appearing 2 years down the line, please don't set an aim that I simply have to get through the examination. All those of you who are attending the session and who are going to appear maybe 2 years down the line, 3 years down the line, 4 years down the line, you have to set yourself a target to maybe get a rank of double digits or a single digit. So like that, you set yourself a target because you have that time and it is absolutely achievable. Okay. Right. For those who are appearing for 2023, Arjun, I would suggest to you follow these lectures along with the additional reading materials and the sources of current affairs. Go for the examination. Current affairs, ideally, as much as you can follow, that is as good as it can get, because then you get into the trend of it, that what is the direction that the entire global geopolitics is following. You get an idea about everything which is happening around the world, and that will give you a significant edge over your competitors, right? Now, while revising, you have to consolidate the last 12 to 15 months of current affairs by continuous revision. Now, this process becomes much easier for those who have been following current affairs for a long time. Please understand, guys, this is not as if this is a required aspect and you are putting tick marks here and you will succeed. No, you are competing, right? It is a competition. You will be facing the competition against even those candidates who have got the habit of studying the newspaper since the school days itself. Many of the candidates that you will come across, they are in a regular habit of reading the newspaper since the school days and so on. So the perspective that they will develop, that is something that you have to counter. Current affairs is not only about appearing for prelims. Current affairs is also being able to provide different viewpoints, different perspectives in the mains examination. So that will come, uh, given the fact that if you are following it for a longer period of time. Many of you have that kind of a tendency that I'm going to appear for the examination in 2025. So current affairs, I will start from 2024. That is an absolutely wrong approach to take. If the moment you start dividing the dynamic portion from the static portion, that is the end of the story. In that ways, neither will you be able to capitalize on dynamic, neither will you be able to capitalize on the static portion. Okay. No, Unnati, if you are already going through the Byju's book and the lectures, everything, don't go through the NCERTs, not needed. Pushpendra, not in the present day and age, I would not recommend you to make the notes of current affairs. The monthly magazines that you have, more than sufficient to give you an idea about what is going on around the world. Keep revising them as significantly or as frequently as possible? No, Richard, please don't do that. See, all of those, and many of you have written to me as well with regards to that. We have the CNAs as well, we have the newspapers as well, we have the classes as well, we have the webinars as well, we have the YouTube sessions as well. What do I follow? What do I leave? I have only 24 hours a day. I always would suggest to you, prioritize. Newspaper is an absolute must. Studying general studies on a daily basis is an absolute must. These two need to be fulfilled. If you have time which is left, then look at newspaper analysis, then look at webinars. Webinars and newspaper analysis, anyways, will be available to you in a recorded format. So that is something which you can finish up very quickly. There is no safe choice when it comes to an optional subject, my dear friend. Any optional that you choose, your aim has to be in the top 20 of that optional in the entire country. Any optional that you choose, be it anthropology, be it geography, be it sociology, be it public administration, be it PSIR, any optional that you choose, that has to be your aim. Why? Because if you are not within the top 20 of that optional in the country, you will rarely be able to find yourself competing amongst the top guys, and maybe you will have a rank which is very insignificant, and thereby maybe the adequate services will not be allocated to you. So always have that kind of an approach, that kind of a fighting spirit. Okay. VD for 2024, after you have covered the entire, see, I will provide you, after, as we come to the end of the sessions, I will provide you with the adequate measure that you can follow with regards to revision. And that can include either with the NCRTs or the tablet videos. Now, all those of you who have the tablet videos of geography, the the tablet videos are significantly detailed. Now, there in the tablet video, most of you would be having the tablet video where I'm there, and I have ensured while recording those tablet lectures that it is in so significant detail, much significantly detail as compared to any of the NCRT books. There I have used the compilation of many of the materials. We have close to around 104 plus hours of, or 100 plus hours of geography lectures available on tablet. You can use that as revision tool as well. So it depends upon you guys. What is your priority? What is your preference? What is it that you like to study? Shape your strategy accordingly. As I told you, regardless of how you frame that question, that I'm appearing for the examination in 2026, do I start reading newspaper now? I'm appearing for the examination 2025, do I start reading news? Newspaper reading should be started as soon as possible. If possible, start from today itself on a daily basis. Okay? Yes, Tanu, you can do that. Now, after this, we come to the portion of plate tectonic theory. Now, this is a theory which was developed in the late 60s and the early 70s as well. And this is a theory which is able to explain the movements that happen across the Earth's surface, and thereby is able to explain many of the different phenomena that we experience on the surface of the planet. Now, what is this plate tectonic theory? By the way, this plate tectonic theory was not propounded by one individual. It is a combined effort of many different individuals, many different geographers, which have come to the fore. For example, you have Wilson, Tuzo Wilson, you have Mackenzie, Parker, Morgan, all of them, they have contributed in their own way in deciding or in postulating this plate tectonic theory. Now, this plate tectonic, why the name tectonic? It is derived from the term tectonique. So basically, it is derived from the term tectonique, which means building. So that is where the term tectonic has been derived from. So it talks about the movement of the plates, the existence of the plates, and how they end up behaving with respect to each other to give rise to various different phenomena. So when we talk about this plate tectonic theory, basically it talks about the fact that lithosphere is broken into various different parts, which we refer to as plates. Now, when we talk about lithosphere, again, I would like to reinforce the fact that lithosphere talks about the portion of the crust and upper solid mantle. Okay, that is what the lithosphere is divided into. And basically, how do we get to know that lithosphere is divided into plates? We get to understand that by studying the seismic waves, the waves which are generated whenever an earthquake happens. That is when we get to understand that, okay, this is a plate boundary, this is where a plate exists, and so on. Now, these plates, they move over the region of asthenosphere, right? So this molten mantle that you see, that is basically the semi-solid asthenosphere. Semi-solid asthenosphere. Okay, so they keep on moving over that asthenosphere, and these plates move with respect to each other. Now, why will they move in the first place? So that movement is basically generated as a result of the convection current which is present in the interior of the planet in the region of mantle. So the movement is generated because of the convection current. Convection current present in mantle. Excuse me. So that is why the movement is generated. Now we have taken a look at why that convection current exists with the help of the convective current theory provided by Arthur Holmes, where we looked at the fact that it is the residual heat which is provided in the region of the mantle that generates this particular convection current in general. Now, overall, if you take a look at the entire globe and the entire world, this is the classification in terms of the plates that you observe, right? Now, in each of these plates, in fact, in majority of these plates, you will observe, in majority of the plates, you will observe that they consist of both continental crust, continental crust, and oceanic crust. Most of them, other than a few. For example, if you consider the larger ones, the Pacific plate is the one which consists of only oceanic crust. This is the Pacific plate. It consists of only oceanic crust. Nazca plate that you see consists of only oceanic crust. Then Cocos plate that you see again consists of only oceanic crust. Yuan the Fuca plate that you consider oceanic crust. Filipino plate at one point of time was again only oceanic crust, but now you have the emergence of islands there, indicating some amount of continental crust also being present. Otherwise, if you observe North American plate, you will observe the presence of continental crust here and oceanic crust here. South American plate, continental crust here, oceanic crust here. Indian plate, continental crust here, oceanic crust here. Similarly, for majority of the plates, you will find that there is a combination of both continental as well as oceanic crust which is present. Now, what are these plates, by the way? plates are the divisions, or for example, think about it, that if you think of the entire lithosphere, this lithosphere is broken into multiple different subparts. These are your plates. So if you consider this to be lithosphere, right? These are a part of your plates. Okay, so that is what determines and generates the plate tectonic theory. Now, why is it that the plates end up moving? Why is that movement generated? So the answer for that is very simple. So the plates will move because of the convection current. Because of convection current. Present in mantle. Okay, so for example, for this, in order to understand this, think about a very basic experiment that you can again conduct at your house itself. So, for example, suppose take a jar of water. Okay, put it on the flame, and let's suppose you have filled it up with water. On top of that water, let's suppose you have put two wooden blocks which are floating. You have put two wooden blocks which are floating, that is A and B. Now, if you heat it up, now do one thing. Try this at your home sometime. You can take wooden blocks, thermocol blocks, anything. Put them together and then start heating it up. You'll find that the bubbles, they start rising. The bubbles, they start rising. And eventually, there's a kind of a bubbling motion which is present. After some time, you will find that as the bubbles keep on rising, due to the convection current which is generated, the plates, or rather blocks A and B, they shall be drifting away from each other. Something very similar is at play even in the region of mantle and crust. And basically, mantle and the portion of the lithosphere in general. So as you have the convection current present in the mantle, that convection current has, or rather, the horizontal component pushes the plates with respect to each other. Okay. Now, here you can have three kinds of motion. Either the plates will move towards each other, the plates will be moving away from each other, or the plates are moving parallel to each other. We will take a look at how, but before that, this is a kind of a recap of the things that we have already studied, or that things that we have already gained in information with regards to the theories that we have covered till now. So here, if you will observe, you have the convection cell, right? Convection cell which is present in the mantle, and you will observe that the horizontal component of that convection current, that is what is moving the plates away from each other, leading to a thinning of the lithosphere in the region here. The lithosphere becomes significantly thinner. Okay, it becomes very, very thin, and eventually this is where, as it becomes thinner and thinner, this is where eruptions will happen, and you have the mid-oceanic ridge getting created there. Now, how is it that basically this thinning action happens, or is it the case that it will only happen underneath the water body, or is it something that can happen even underneath the continents? Because that convection current can happen anywhere, everywhere. Why do we consider that only underneath the water body? It can happen under continents as well. So let us understand why is it that it happens only in a certain manner. Let us see. So for this, again, I would take you back to your childhood days where basically, I don't know how many of you have done that, but over a candle, the flame of the candle, many of the times you would basically have tried melting a plastic or a plastic scale and observe how the plastic scale melts. It is not that if the plastic scale immediately starts dripping. If let's suppose you have a candle, okay, and that candle, let's suppose, has a flame. On top of it, if you put a plastic scale, what will happen? Now, initially, you will observe that the plastic scale, if you pull it from both sides, as and when it gets heated, if you pull it, it starts thinning significantly till it becomes very, very thin and breaks apart, right? Something very similar that we saw in the case of convection current theory as well. So basically, just like this, suppose we talk about a continent. Take a case of continent like Africa. Let's suppose a random continent that we take. Now, here in that random continent, this is the top view that we are looking at. Let's suppose it is in this region here where you have the vertical presence of the convection currents. Let us assume that it is here that you have the area experiences the vertical convection or a vertical component of convection current. Now, and let's assume all sides of it is surrounded by ocean, just like in the case of Africa, ocean, ocean. Let's assume. Now, here, initially when that convection current starts to act, when it starts to come into play, the thing which will happen is very, very similar to what happens with the plastic ruler. The land in that portion starts getting softer. It starts getting thinner as it is stretched from both ends. It will start getting thinner and thinner and thinner. Now, here also assume that it starts getting thinner. At the same time, the land is being pulled away from both ends because of the horizontal component of the convection current. The land is being pulled away from both ends. Now, what will happen? Observe that there is a significant thinning of the lithosphere, right? Now, imagine if this thickness is what represents the continental crust, over a period of time, when there is that thinning action which takes place, that will basically thin it out. The surface will sink a bit and the lower surface will also bottom out, and eventually it will be stretched significantly. As a result of that, ocean water will come into these areas. And this continent will break into two, and that narrow portion, which is experiencing the vertical portion of the convection current, that will be filled with oceanic water in general. Now, again, that is filled with oceanic water means that portion where that convection current was happening, that is now under a water. Now, if it continues, the convection current continues, what will happen or what phenomena will you experience underwater? You will experience the breaking of the crust and eruption of a volcano through a mid-oceanic ridge. So that is how, in majority of the cases, these convection currents, when they start driving, that is when eventually the crust thins out, and that is when the waters from surrounding regions, they come in, and you have a development of a mid-oceanic ridge which observes active volcanism, and thereby again the seafloor starts spreading away and the continents, they do drift. Now, in that entire sentence that I just said, if you are awake and if you are awake and alive, the entire sentence that I just said, in that entire sentence, I have made use of the convection current, I have made use of the spread of the seafloor, I have made use of the drift of the continents. All these three theories were rejected. But all these three theories, some or the other portion of it, that comes into place to justify what is happening across the planet in real time, which tells you that some part of all these theories that have led us, or that has in general led us to a greater or a better understanding of what we consider as plate tectonics. And this is a question which UPSC has asked in optional portion of geography quite significantly number of times. And then now UPSC has been asking this in the portion of general studies as well. For the past 2 to 3 years, it has not been asked, but it has 2 years rather. 3 years back, this was asked. So the question which UPSC frames is, how is it that the theory of continental drift, seafloor spreading, and convection current helps us understand the theory of plate tectonics? So thereby, you have to elaborate upon the aspects of the plate tectonic theory and how some portion of it justifies seafloor spreading, some portion of it is justified by the convection current, and some portion of it is justified by the drift of the continents. Now, in this, here, when we basically PYQ, we have already discussed one. If you were not present in the session, please take a look at the annotations of the PPT. Again, more PYQs we will discuss. Okay, please don't keep poking around about PYQs. We will discuss all the PYQs. We will be discussing how to write the answers as well. Okay, right? Now, here, this is why the plates end up moving. So the plates basically, when they end up moving, that is basically because when you have a particular kind of a plate, when they are pulled apart. Why are they pulled apart? Because of the convection current. When they are pulled apart, they start to thin out. When they start to thin out, that is when water from the nearby regions, they come in, and that portion lies underwater. Again, as the thinning out continues, eventually the plate is thin enough for that portion to observe the creation of volcanic eruption and formation of a newer crust, as has been explained by seafloor spreading as well. Okay, this is the aspect of plate tectonic theory. Now, when we talk about the movement of the plates in different form can move only in certain manner. The plates can either move towards each other, they can move away from each other, or they can move parallel to each other. How is it possible? We can understand that the plates can move away from each other. But how is it that we can say that the plates are moving towards each other? Or how is it that we can say that the plates are moving parallel to each other? So it is all initiated by the convection current. So if we consider plate movements, right? If we consider the plate movements, let's suppose here we consider the portion of two plates, or rather four plates. Let's consider A, B, C, and D. Now here, if you have a convection current which is present underneath B and C, right? So if you have a convection current which is present underneath B and C, then, and let's suppose another plate is there, that is plate E. Now, there is a convection current, there is a convection current underneath B and C. A and D do not experience a convection current. So if we consider the movement of B and C, are they moving towards each other, away from each other, or parallel to each other? So if we consider B and C, they are moving away. Very good. Moving away from each other. Okay. Then, if I consider the plate A and B, or if I consider C and D, what is the movement? Now, B is moving towards A, C is moving towards D. So, they are moving towards each other. Towards each other. Now, if I consider the movement of C as compared to E, in that case, C is moving in this direction. Now, it is neither moving towards E nor is it moving away from E. So, that is where this is also what is referred to as moving parallel to each other. Parallel to each other. No, Rohan, that was taken from the convection current theory in general. So, this is the aspect of the movement of the plates. That is why we can say that it is the convection current within the mantle which drives the plates towards each other, away from each other, or parallel to each other. Now, when the plates they move away from each other, that is what we refer to as divergent plates, right? And it is the boundary is also referred to as the divergent plate boundary or the divergent plate margin in general. When the plates they move towards each other, that is what we refer to as the convergent plates, right? And the boundary is referred to as the convergent plate boundary. For example, I'll give you the examples of all of these. We will study each of these in significant detail as well. Don't worry about it. And then parallel to each other, transform plates. Let us pick one by one each one of them. Let us try to understand what they are. Now, we start with the convergence of these plates. Let us understand how is it that there is a convergence of plates which is happening. So we have seen earlier that for convergence, you don't need the convection current to drive each one of them towards each other. You can have one plate which is experiencing a movement like this. The other plate might be static, but it will be a collision, isn't it? Now, suppose here I have put another plate. Let's say F. Now, if there's a convection current underneath F and A, now in that case, if I consider F and A, now A will be moving towards B now. So this is a kind of a convergent plate movement, isn't it? So like this, you have consistent plate movements. Now, in the case of the convergent plate boundary, you will observe that as the plates they collide with each other, one of them that starts sinking or rather subducting down. As they start subducting down, eventually you will observe that one of them is the one which climbs above the other one, the heavier one sinks down, right? This is the kind of convergence. Now, in this case, part or the portion of one plate that is getting destroyed as it is sinking underneath the other one, portion of one of the plate is getting destroyed, isn't it? As it is getting consumed underneath the other one plate is getting consumed and destroyed. That is why convergent plate boundaries, they are also referred to as destructive plate margins or boundaries. Now, in the case of convergence, always remember one thing. It is always going to be the heavier plate which is going to sink, and the lighter plate is going to stay on top, and the heavier plate, owing to the influence of gravity, the heavier plate will continue to sink. That is always going to be the case. So, always here we can write the aspect of the how do plates subduct rather, right? So here, if you will observe, the heavier plates will always sink or subduct. They will always sink or they will always subduct. Why? Owing to the gravitational pull of attraction, due to the gravitational force. Because we know that something which is heavier, that will experience greater gravitational pull. Something which is lighter will experience slightly less amount of gravitational pull, isn't it? That is something which is at play here as well. Now, when we consider the different plates, we do know that you have different types of crust which is present. Let us assume that we consider continental crust and oceanic crust. And oceanic crust. Now, out of these two, which do you think will be the one which will be sinking or subducting underneath the other? Which of them? Okay, beautiful. Okay, now few of you. Okay, okay, fair enough. Out of these two, first of all, give me the answer. Out of these two, which do you think is heavier? Is it the continental crust which is heavier or the oceanic crust which is heavier? Which of them is heavier? Continental is heavier. Why? All those who are saying continental crust is heavier, could you let me know the reason why it is heavier? Because of thickness. So anything which is going to be thick is going to be heavy. If that is the logic that we are following, then tell me, if I have a thermocol block, let's say, which is 1 meter thick, right? And I have a steel slab, steel or rather iron slab, which is 20 centimeter thick. Let's say this is steel, this is thermocol. Thermocol is thicker, steel is thinner. Which do you think will be heavier? All those who were saying that it is heavier and hence it is thicker, hence it is heavier. Right? Now everybody is saying steel is heavier. The same thing when I said in the second session, either you had your mind somewhere else. Continental plate will have more solid material compared to oceanic plate. Why? Now, in that case, thermocol will have more solid material as compared to steel because it is thicker. Can we say that? Can we come upon that conclusion? If I take 1 kilometer thick sponge, 1 kilometer thick sponge, and I take 1 meter thick steel, which will have more solid material, etc. The amount of solid material is never decided based upon thickness. For all those Einsteins who are sitting here, all those Nobel Prize winners who are sitting here, let me tell you a very basic fundamental of science, that it is not about the thickness of material which will ever decide the weight of the material. Always understand, with significant amount of humility, let me submit before you. Now you decide whether it is right or incorrect. Always understand, weight is decided by density, density of material, right? Now, oceanic crust is always going to be heavier is heavier due to higher density. Now that is forcing me to ask a question out of you guys. And I'm very tempted to ask this question. How many of you managed to do the map pointing that I gave to you yesterday? Hmm. Okay. Okay. So few of you did that. The equal number. So I see the names who have done that. Basically, you are the ones the names who have done that are the ones. Basically, you are giving the correct answer here as well. So all those bright candidates and the bright students who are thinking of clearing the examination sometime in the near future, I would suggest to you, please kindly go back and revise the previous ones because we have discussed this already. But nonetheless, now after the session, I hope that you find some time. I know your schedule is very packed and it is very, very full, very busy. Maybe Prime Minister Modi has got more time than you guys. Having said that, please take out some time in your daily schedule, packed schedule, revise the previous sessions. Just sitting in the session will never help you accomplish anything. Now, let's end the discussion there. Let's talk about which of them is heavier. It is the oceanic crust which is heavier. Again, I will reiterate why. Because it has got greater density. Why? Because it is made up of rocks primarily such as basaltic rocks. Right? So, because of basaltic rocks. Basaltic rocks. And what is the density of it? Density is close to around 2.9 to 3 gram per centimeter cube. Vinay, my dear friend, no need to submit the map pointing anywhere. We are adults now. I hope that is clear and it is only for your revision, right? It is not about submission. Okay. And when we talk about continental crust, even though it is thicker, it is lighter. Why? Because of the presence of granitic rocks. Very good, Pranay. Granitic rocks. So here you will have the density as 2.6 to 2.7 gram per centimeter cube. So always oceanic crust is the one which is heavier, right? This is something you always have to keep in mind, that always oceanic crust is going to be heavier. So amongst the continental and the oceanic crust, if they are converging, which is the one which will subside? It is going to be the oceanic crust. Okay. Now let us take a look at the convergences. Abhijit, both of them are continental crust. Okay. Don't think about it that Eurasian plate is an oceanic crust and Indian plate is a continental crust. That is why I tell all of you that chew one amount of thing at a time. Don't consume the whole food at a time. Slowly and steadily we get there if you allow us to go as per what we want. So let us take a look at the types of convergences. Now we have different types of crust. We have the continental and the oceanic crust. So there can be only three types of convergences. So the three types of convergences which can happen is oceanic, 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 oceanic continental, and continental, continental. Okay. So these are the three different types of convergences which can happen. Let us take a look at all these three kinds of convergences. Let us try to understand what is the phenomena which unfolds and what is it that happens. So first of all, in wherever you have the oceanic crust, it is going to be the heavier one. Now, what if there is a condition of both of them being oceanic? In that case, which will be the heavier one? When you have both of the crusts which are colliding, which are oceanic in nature, in that case, the older oceanic crust is going to be the heavier one. Older oceanic, or rather, simply I will write older crust is heavier. Okay. Why is it that older crust will be heavier? So let's compare. If suppose there are two oceanic crusts, one has been created 300 million years ago, one has been created 100 years ago. The one which has been created 300 million years ago, that would have had sediments deposited in it. It would have had presence of sedimentary rocks where various oxides would be formed, etc., etc. That would be increasing the weight of the older crust. That is why the older crust is always heavier as compared to the newer crust that you observe. Now, when we take a look at the types of convergences, we will first of all be starting with the convergence of oceanic plate and continental plate. For example, which plate are we going to take for an example? So, for example, I will take you to the plate movement here. So, here let's suppose, I consider this Nazca plate and the South American plate, right? Or Pacific plate from North American, anything. Let's assume I consider Nazca plate and South American plate. Now, both of them, they are moving towards each other. So it is a oceanic convergence that we are talking about. Now, in the oceanic continental convergence that we are talking about. So example, Nazca and South American plate. Okay. Now let us try to understand what is it that unfolds step by step. Just pay attention for the few moments and it will be crystal clear. I can assure you. Just pay attention. Don't try to run ahead of your time. Just pay attention to what is being told. You will understand everything. So here, let's assume this is the portion of the oceanic crust. Let us assume that. Now here, let us assume you have a thick continental crust, significantly thicker continental crust is present here. Now, here you have the presence of water as well, because it is an oceanic crust, isn't it? Now, let's suppose there is a convergence which is happening whereby this oceanic crust is getting pushed towards the continental crust. What will happen? Initially, the oceanic crust, because it is heavier, it will try to subduct, or it will try to sink. So here, in the initial stages, this oceanic crust will try to subduct underneath the continental crust. So this oceanic crust will try to subduct. But imagine this is the continental crust, this is the oceanic crust which is trying to subduct. Will that subduction process be a smooth one? No, because we are talking about kilometers of thick rocks, and you have rocks which are rubbing against each other. When the rocks are rubbing against each other, that movement is never going to be a smooth one. That movement is going to be significantly rough. So here, when you have one plate, the other plate which is trying to sink here, observe there will be a deformation in both the plates. So as this plate is trying to subduct, there will be a deformation here as well. Right? So the continental crust will be deformed. But then continental crust is thick, right? Now, as the continental crust is thick, it will experience a resistance. Resistance, force of opposition in simple terms. As the oceanic crust tries to sink, the continental crust will be compressed slightly. Due to that compression, because the continental crust is so light, made up of granitic rocks, you will experience that in the region of the continental crust, you will experience there is a formation of a kind of a fold here. Formation of a kind of a fold here, right next to the margin of it. And this will be covered with water. Now, again, I will ask you, at this point, that is where the two plates are merging or meeting against each other and one is rubbing against each other. Will that movement be like what you see in computers, like a movement of paper and cloths, very simply smooth one? No, it will be a staggered one. It will be movement which happens and again it stops. There is a resistance, force of opposition which builds up, which stops the movement of the rocks. And because of the continuous push which the other plate is experiencing, there will again be a sudden movement. Again, there will be a stop. Again, there will be a sudden movement. Whenever such sudden movements are initiated, there is an energy which is released. And that energy which is released, that shakes up the ground surface, be it the oceanic bottom, be it the continental crust. Both of them, they start shaking vehemently whenever there is that sudden motion or the release of energy. And that shaking of the surface is something that we experience as earthquakes. So that is where in these margins, at these points, you will experience earthquakes. Right? Now, you will also observe that here, basically, you will observe that this is filled with water. Now, in this portion, there has been a deformation, a kind of a depression, a very narrow depression is created. This is what we refer to as an oceanic trench. Oceanic trench. Example, because we have talked about Nazca and South American, here we talk about Peru-Chile trench. Very good. Peru-Chile trench. Okay. Now, all these examples that I'm giving out to you, I expect you to look at all of these in the physical map so that you get frequented by it and you get comfortable with it. So all these, you have to take a look at the map as well. Now, here, one of the plate is sinking down. Now, the oceanic plate which is moving down, this one, which is moving down. Now here, do you think it is only the oceanic slab of the crust which will go down? Or will it bring some amount of sediment, some amount of water along with it as it sinks down? Well, the answer is that this plate, as it starts sinking down, it will be able to bring some amount of sediment, some amount of water along with it. So some amount of that water, sediments, etc., that is brought in the interior of the planet. Now, water is something which very significantly and very quickly melts and, in fact, very quickly vaporizes as well. Now, at a depth of around 160 to 200 kilometers, at around, or 100 to 160 kilometers, at around that depth, the temperature increases so significantly that materials, they start to melt, and the water that was present, that starts getting converted into water vapor or a gas. Now all these molten materials, they will start rising. Molten materials, they will start to rise. Because obviously, molten materials which have the presence of gas, they will always be lighter. So they will start to rise. Now, as they start to rise, they will be heating and melting up the sections above them, and eventually, the gases that are present, they will bring significant amount of pressure, and that will erupt in the form of volcanic eruption. Volcanic eruption. Right? Example, in this region, that is Nazca and South American plate in this region, the example of such volcanic eruption, you have Mount Cotopaxi. Okay? Mount Aconcagua as well, the tallest peak of South America, that is Mount Aconcagua, right? Now, before that, you also have the crust which thickens, and you have a fold mountain which is created because the crust is getting folded. So here you have the presence of fold mountains. Fold mountains. Example, you have Andes. Right? They are the ones which are created as a result of oceanic continental convergence. Now, as these plates, they start going down, they will exert a pull on the rest of the plate as well. How? So again, think about a very common and a significant example that I oftentimes tell the candidates to imagine, that in your childhood days, you would have seen that you would have played with a toy train, right? The toy train which has got an engine and various different bogies attached to it, right? Now, if it is on the table, if you put that toy train on the table, it will be very stable, very happy, very static in general. But do one thing, take it to the edge of the table and hang that engine or the locomotive downwards towards the ground while the rest of the train is on the table. You will observe that slowly and steadily, the rest of the train is also dragged to the ground. Why? Because the gravitational component which will act on the vertically hanging part of the locomotive, that is something which will pull the rest of the train as well. Similarly, the portion of the plate which is sinking, that will have the gravitational pull, and that is something which will pull the rest of the plate as well. That is something which we refer to as slab pull. Slab pull. That is gravitational component acting on the hanging or overhanging plate, pulling the rest along with it. Okay, that is what is referred to as slab pull, where the remaining portion of the plate, that is something which is also pulled down. Okay, so that is what happens in the case of continental oceanic convergence. right? Now, again, I will repeat the entire process. Whenever you have a continental oceanic convergence which takes place, the oceanic plate being the heavier one is the one which will sink. And when the oceanic plate starts sinking, at that point of time, it will create a deformity here. The continental plate will also get deformed. That will create an oceanic trench, a deep oceanic trench at the margin of the continent. And furthermore, the continental plate will be slightly compressed, creating fold mountains at the margins. Example, Andes in the case of South America, Rockies in the case of North America, Atlas in the case of Africa. You have many such examples. Now, as the plate starts sinking, the movement is never going to be smooth. It is going to be staggered. It is going to be very, very rough. And as a result of that rough movement, you will observe what? You will come across a scenario where this rough movement will create a situation. Whenever there is a sudden movement, a lot of energy will be released, leading to significant amount of shaking of the ground surface that we experience as earthquakes. So at all the margins of convergences, you will experience significant amount of earthquakes because the movement is never going to be smooth. Now, furthermore, the plate that sinks after reaching a depth, the materials that will start to melt, they will start rising up. Eventually, they will emerge as a form of volcanic eruption. Moreover, the penetration of water and gases along with, or penetration of water and sediments along with the plate movement, that will make the water vaporize significantly, and that will add to the gases, which will lead with pressure and which will lead to the emergence of materials to the top of the surface. So that is how you have the convergence which happens in the case of ocean and continent. Okay, so that is the case, for example, in the case of Nazca plate and the South American plate, and also in the case of, for example, when we talk about the African, or rather the Mediterranean portion and the Eurasian subcontinent. There also this is happening. That is why in the southern portion of Italy, in the portion of Turkey, in the portion of North America, North Africa, you experience frequent earthquakes. And not only that, this is the reason why in the region of southern Europe around Italian coast, you have a lot of volcanic eruptions. Why? Because of this process. The Mediterranean Sea is closing as the African plate is moving into the Eurasian plate, and that is why you have so many volcanic eruptions also, which do happen, which do take place. Okay. Slab pull is basically when you have the portion of the overhanging plate, due to the gravitational component, it is able to pull the rest of the plate with a significant force, and that movement starts to accelerate. So that is what is slab pull. Okay. Now, then what happens when you have two oceanic plates which undergo convergence? Now, in this case, which will be heavier? In this case, you will always end up finding that the older plate is heavier. Always. Right? Now, let us understand what happens in this case. So, it all happens underwater, first of all. Now, here, if I consider this, let's suppose another plate. Now, as there is a convergence which is happening, again, something very similar will happen, that both the plates will get significantly deformed. Both the plates will get significantly deformed. So here again, you will observe what? The existence of oceanic trench. Oceanic trench. Example of such oceanic trench, you can take the case of Mariana Trench or the Challenger Deep, which is the deepest point underneath water across the globe with a depth of around close to 11 kilometers below sea level. So that is where you have the Mariana Trench. Okay. Now, locate all these portions, guys. After the session, locate all these areas where they are. This will always augment your understanding. It should not be that after the session ends, now I can watch IPL, now I can relax because I have studied enough. No, it should not be the case. Always try to follow it up as soon as possible. Okay. Now, here, when it starts going down, at that point of time, at the plate margin, when one of them is rubbing against the other, just like the previous one, here also there will be a rough movement, a kind of a staggered movement. And whenever that staggered movement happens, think about it. It starts to move and it is stopped because of opposition of kilometers thick of rocks. Now these crusts, these appear to be very thin on the screen in front of you, but in reality these are 10 kilometers, 20 kilometers thick. So 20 kilometers rubbing against another 15 kilometers thick rocks, it is never going to be a smooth movement. It will offer some opposition. Slowly and steadily, energy will build up, and suddenly there will be a staggered movement. Now, whenever such kind of a movement will happen, it will create a lot of disturbances and a lot of energy will be released. And that is where, in this point, at this area, you will experience what? Earthquakes. Earthquakes will be generated. Now, in the earlier case, we observed the presence and the formation of fold mountains in the margin. Here, will we experience the presence of fold mountains? The answer is no. We won't experience the presence of fold mountains or the formation of fold mountains. The reason is very simple. The continental crust is thick, due to which some portion of it can get folded into a kind of a mountain. Oceanic crust is thin. It does not have a scope to get folded itself. So that is why here you don't observe the formation of any fold mountain. So here no fold mountain is observed. No fold mountain. Okay. And also here, after a point of time, as water, sediments, etc., they start sinking along with the plates. At a particular depth, the materials, they will start melting. And that is when the molten materials, they will start rising up as well. Now, as they rise up, they will lead to what? Volcanic eruptions. Volcanic eruptions where? Volcanic eruptions underneath the water body, right? Underneath the ocean, there will be a volcanic eruption which will happen. Okay. Now, here, these volcanic eruptions, they give rise to underwater volcanoes or underwater mountains as well. As the volcanic eruption keeps on continuing, eventually what happens? Eventually, after some time, you will observe, if it continues to happen, the landform will keep increasing in size till a point will come when it will emerge from the surface. When it emerges from the surface, that is when you have the formation of volcanic islands. Formation of islands. Example, Philippines, very good. Very good. Indonesia. Okay. So that is what happens if it continues to emerge. That is how in the region of Philippines, in the region of Indonesia, you have thousands of islands which are present in that particular area itself. Okay, so that is how in the case of an oceanic convergence, we experience volcanic eruption, we experience the activity of earthquakes, we experience the action of the oceanic trenches getting created as well. So, in a way, can we not say that whenever there is an oceanic plate which undergoes a kind of a convergence, that oceanic plate's convergence will always lead to volcanoes, earthquakes, trench formation? These three are common in both of them. That is volcanoes, earthquakes, trench formation. If there is a continental plate involved, fold mountain might come into existence. If there is no continental plate involved, no fold mountain, because the crust of the oceanic plate is very thin and it has got higher density. It is not foldable easily. Okay. Now, then here we have another kind of convergence, that is continental convergence. Now, in this case, both of them have lower density, but still the older plate is the one which will subside. So here, older plate sinks. Yes, Aman, it will, but we'll come to it when we come to earthquakes. Older plate subducts. But then, in this case, both of them are so light, right, that here the convergence which will happen will not lead to a significant amount of subduction of the other one. Imagine it, right? All those Einsteins in the class who had that great thought, that thought-provoking idea that because something is thick, it has got to be heavier. Don't compare it to humans, because if humans are thick, they will be heavier. Don't compare it to us humans. Think about it in a different aspect. These are light materials. The continental crust that you are talking about, they are very, very light materials, right? So here, when we talk about it, basically, let's suppose you have one continental plate converging with another continental plate. Okay? One continental plate converging with another one. Take the case of Indian plate and Eurasian plate. Indian and Eurasian plate. Okay? Now, when they undergo a kind of a convergence, imagine, as suppose, think about it, that two vehicles when they collide, the light vehicles, the ones, take the lighter ones, for example, suppose that, take the case of two Maruti 800s, the older models of these Maruti 800s, the older vehicles. When they collide, if ever you have seen a collision, please don't carry out a collision just because I have said so, right? Because he said so, I had to make my vehicle collide with something. No. If you have ever seen that collision, you would observe that there's a deformation of the vehicles. Neither of the vehicle is climbing over the other, because nobody is heavier than the other. Both of them are light. They get deformed, they get compressed quite significantly. In the same way, here, when they collide, there is a deformation. The crust starts to thicken. Some portion of the heavier plate that will subduct very slightly, very ever so slightly. So in this case, when there is a convergence which will happen. Now, by the way, here again continental plates are involved, which has got lower density. So when there is a compression, will there be a formation of a fold mountain or not? What do you think? Will there be a formation of a fold mountain? Very good. Absolutely yes. So in this case, again, you will find that the crust thickens and you have the formation of a kind of a fold mountain. And as that convergence takes place, some portion of the heavier plate will subduct ever so slightly, very thin portion will subduct, but the remaining portion will be involved in crustal thickening and deformation. Right? So you will observe crustal thickening, and deformation. In fact, so much amount of energy and compression will be utilized here that all the rocks which you will find in this region, this is how you interlink the topics. All the rocks that you find in this region, most of them will get converted into metamorphic rocks. So because of this, the huge pressure leads to metamorphic rocks, formation of metamorphic rocks. Now, in the second module, you would have seen that, for example, in the region of Himalayas, the crust has thickened to almost 70 kilometer plus. That is how thick the crust has become. So obviously, that much amount of crustal thickening will make it absolutely impossible even for molten materials to be coming closer to the surface. So even if you consider some portion of the plate which subducts, the crust is so thickened, even if some portion of it melts, it will never be able to rise and break through that particular thick crust. So, no volcanic eruption. Why? That is because of two reasons. One is crust is very thick and composed of highly compressed rocks. Highly compressed rocks. And what is the second reason why there won't be a volcanic eruption? That is because in the earlier scenarios, you would have observed that some part of that water that penetrates, which facilitates that melting and vaporization. So in this case, there is no penetration of water. That is why no presence of gases as well. Unless and until there are gases, it won't rise and break through the surface. So lack of penetration of water, lack of penetration of water means no gases, right? Now, as one of the plates starts subducting, will that motion be smooth or will it be rough? We are talking about now 30, 40 kilometers thick rocks which are rubbing against each other. Will that be a smooth movement or not? It will never be a smooth movement. Never. It will always be a very, very rough movement. And that is what gives rise to very powerful and high magnitude earthquakes. So in these regions, powerful earthquakes. Example, the earthquakes that you observe in the Himalayan region, Nepal, etc. That is where you have this kind of a convergence. And on top, you will have fold mountains. Example, fold mountains. Example, Himalayas, Alps, etc. Okay? So that is what happens in different types of convergences that we come across: oceanic, oceanic, oceanic continental, and continental, continental. In all the convergences, you will observe earthquakes. In the case of continental convergence, you will observe fold mountains. In the case of oceanic convergences, you will observe trenches, volcanic eruptions as well. Okay, that is where we'll restrict the session for today. Tomorrow, when we come, we will talk about the formation of Himalayas and earthquakes and volcanoes. Okay, so few of the questions we will take. In the meanwhile, we have taken many questions, so few of the questions we will take. Okay, Everest is a fold mountain. Yes. Thanks for the compliments, Kunal. Kind words from your side. Are all mountains created like this? No. No. Fold mountains are created like this. You have volcanic mountains, fold mountains, and there is another kind of mountain, that is the block mountain. We will talk about it when we talk about the next module. Today we won't have the map pointing. Tomorrow I'll try to give you. Hawaii is an example of a volcanic mountain. Yes, Hawaii is absolutely, Pranay. Geography is something which drives the portion of modern history, right? So from advent of Europeans to the defense of the or the kind of attack in India from the waters to the portion of the defense of the peninsular region, everything has geography inscribed in it. Thank you everyone for the kind words. I hope that this is something which is clear. I'm trying to take it as slow as possible, guys. We will try to pick it up later on. Don't worry. As of now, my only intention is that you should, after the session, you should have some kind of inkling that what we are talking about. And I would request all of you, all those portions that we have given here, please refer it to the map. Please don't think that today there is no map pointing. Refer to these. Where is Mariana Trench? Look at the various portions around Pacific Plate. You will have the plate boundaries in the annotations of the PPT. Use it with the physical map. You will emerge a much stronger candidate. Trust me for that. Okay. Um, due to okay, a little bit about collide plate due to. Plates collide or plates move due to the convection current, Risha. That is the only reason. Yuvraj, tomorrow we will continue the entire module that we had to cover today. We will cover it tomorrow. After the session, Suraj, I would suggest you look at the annotations of the PPT and just ensure whether you have understood everything or is there any doubt which is prevalent. Just look at that. Sugana, in making volcanic eruption, the materials melted, which is from the mantle. Yes, that is true. Why the older crust is heavier? Because over a period of time, there is a formation of lot of oxides. There is a formation of lot of deposits. All of them, they add to the weight of the crust. Why underwater mountains increase in size? It is not as if the existing mountain you put underwater, they will inflate. No, it is not a balloon. It is the underwater volcanic eruption. If the volcanic, as the slab pull happens in the earlier case, as the slab pull happens, more materials will start getting melted. More materials melting means more volcanic eruption. Hence, you have the size increasing. X, Y, all the aspects of convergences are very relevant for your mains examination. Prakash, that is the example of divergence, the portion of Africa dividing insignificantly. That is the example of divergence. Okay. Devansh, how to develop analytical thinking for mains? That will happen, Devansh, once you have developed an in-depth idea about the basics. See, the questions in the mains examination nowadays, they don't like candidates who rote learn, who mug it up and vomit it in the exam. No. So that is where the more you are frequent or more frequently you are looking at the portion of the current affairs, other subjects as well. Slowly and steadily, after you have completed the syllabus, you will develop an insight where you will be able to interlink the various subjects. The moment that comes into play, that is when mains will be easier for you. That is when you will be able to paint a larger picture. But it will come slowly, my dear friend. For that, you need the help of current affairs and the other perspectives as well. Present active and passive boundaries are the ones, active are the ones where still that movement is happening. Passive is the one where earlier a movement used to happen, but now there is no more movement. Okay, that is active and passive. Sani, apologies for not being able to take the questions, but please put forward the question if you want. And Biswajit, why only few portion of continental crust subside in case of no significant portion subsides? Take the case of Indian plate subsiding and subducting under the Eurasian plate. The entire region is subducting in different speeds in different areas which is present. Okay, how actually these plates formed in litho? So the lithosphere, it is not as if plates are formed in lithosphere. The lithosphere is divided into plates. How? So that particular lithosphere is broken into various different parts. Why? Depending upon the convection current. The convection current is the one which breaks the lithosphere, as we have discussed earlier, just like the breaking of the plastic scale, just like that. Okay. How the subduction stops, the moment the convection current driving this movement stops, the subduction will also stop. Pritham, as of now, for you, I would suggest that please go through the PPT as well as the additional reading materials. Any portion which is unclear, refer to the tablet videos. As of now, don't take a look at anything else. That should be more than sufficient. Mantle plume, we have not come to mantle plume, my dear friend. Okay, so we meet again tomorrow, guys. Till that point of time, take care of yourself. Goodbye. Thank you and good night.